Hello everyone. Today I'd like to talk about the periodicity and boundedness of the absolute recurrence relation by using graphic method. The definition of the absolute recurrence relation is as follows, and here C is the constant. We'll discuss C larger than 0 in this section. We'll discuss three cases. C equals to 1, C lies between 0 and 1, C is larger than 1. When C equals to 1, the recurrence relation has the period 9. The proof is attached in the project, and I will not show it in the presentation since we kind of did this work. Just now I mentioned the graphic method. So what's the graphic method? The sequence can be written as follows, and we can visualize the changing trend of the sequence. That's exactly what the graphic method is. Also, how to interpret each graph is very important. Here to see if the sequence is bounded, we will check if the graph has an upper bound and lower bound. To see if the sequence is periodic, we check if the graph has repetitive shapes. Also note that in the following graphs, x equals to a sub 0 and y equals to a sub 1, both of them are initial values. Now we step into C lies between 0 and 1. At the very beginning, we don't know where to get started, so we just randomly choose the initial values 5 and 7 and parameter C 0.5. There are two observations in these two graphs. First, both of these two graphs seem to be periodic, but in fact, they are not. So we introduced a term called quasi-periodic, which means the graph shows a seemingly periodic pattern, but actually is not periodic. Also, we can see that the initial values in these two graphs are very different, but they still show a very similar pattern. So I guess if I choose another pair of initial values, the pattern of the graph will still remains the same. To validate my guess, I test more cases. And surprisingly, all of these three graphs shows the similar pattern. And I add an extreme case that initial values are equal to each other, and then the shape is still similar to the previous ones. In the above 6 graphs, the parameter C remains to be same, that is 0.5, and initial values are very different, so we can come to our first summary, that is the parameter C dominates the shape of the graph, while initial values have very little impact on the shape of the graph. This is very important to our next section, how the shape changes as C goes from 0 to 1. Here we select initial values 5 and 7. And we don't have to worry about them since the initial values impact on the shape of the graph is very little. Also, to clearly compare each graph with distinct C value, we choose to set each graph to 5 pixels. And in this graph, there are 5 pixels in total, and this is the first pick, this is the second one, and so on and so forth. Also, to compare each graph, I need to focus on another value, that is the ultimate position, and this one. When C equals to 0.1, this value is 8,000, and then 2,000, 400, 200, 140, 80. And we see the width of each quasi-periodicity narrows when C becomes larger. Now we come to our second summary. In the above 6 graphs, each graph seems to be periodic as C goes from 0 to 1. However, after testing each value on the graph, the sequence is not periodic. So we have the conjecture that when C lies between 0 and 1, the recurrence relation is bounded. What happens to C is larger than 1? The first pair of value 1.01 and 1 is selected. Both of the graphs shows an incredibly elegant pattern. The first graph is quasi-periodic, and it's not surprised to see such an elegant graph, since the number 1.01 is pretty close to the number 1. This should show a similar pattern. Another pair of values, 1.05 and 1.09. These two graphs are very chaotic, and it seems that there are no rules in it. But anyway, both of them are bounded. This is an interesting example. When c equals to 1.09 and 7, the sequence still bounded. But after adding 0.003 to the value c, the sequence becomes unbounded. There's a very little gap between these two values, but these two graphs show a very different pattern. So what happens to the small gap 0.0003? Until now, we are not very clear about the small gap. So if you have any ideas or comments, please feel free to share it with us after the presentation. Also, in the second graph, when c equals to 1.1, the sequence is unbounded, and also guess that the value 1.1 is the boundary value between the unboundedness and boundedness. I further test several cases, 1.2, 1.3, 1.4, 1.5, and actually it doesn't make sense. The graph is sometimes unbounded and sometimes quasi-periodic. So until now, we're not very clear about the property of the sequence when c lies between 1.1 and 2. So maybe it's our future research direction. When c equals to 2, we observe that the straight line will extend to infinity when n goes to infinity. So we can say that the sequence is unbounded. When c is larger than 2, the sequence is unbounded as well. The reason is as follows. Since this inequality holds, and this sequence is unbounded when c equals to 2, then the sequence is unbounded when c is larger than 2. Ultimately, I want to make an overall conclusion about the periodicity and boundedness for the following two recurrence relation forms. For alternating recurrence relation, when the pair of value bc equals to the following values, the sequence will be periodic and thus bounded. For other cases, the sequence is not periodic. For absolute recurrence relation, when c equals to 1, the sequence is periodic. When c is larger than or equal to 2, the sequence is unbounded and thus not periodic. For other cases, we have conjectures for c lies between 0 and 1, and the interval 1.1 to 2 is a mystery.